Thanks very much. I actually wanted to start with a little story about an experience that I had with AI about a year ago when I had a couple of relatives come to visit me from Hungary. And they've lived in Hungary their entire lives. They speak Hungarian. They speak some English, enough to hold a simple conversation, but not to kind of know all the complicated words that they need to say, and I don't speak Hungarian. So as we were trying to talk to each other, periodically they would, need to try and explain themselves a bit better, and they did something that many of us do nowadays. They pulled out their smartphone and they spoke a word or a phrase in that in Hungarian, and it would translate it into English, and it was pretty much right. And as somebody who's been working in natural language processing for about 15 years now, I just thought, wow, this is amazing, because when I started in this field, this was basically something that we had on Star Trek, right? We didn't have this in real life. It's not just that particular technology. I'm sure many of you are familiar with other kinds of natural language processing tools like automatic spelling correction and text completion, large vocabulary, automatic speech recognition, voice-activated search, and most recently, voice and natural language activated personal assistants. Right? So we've come a very long way, and we have all of these really great tools. So what I'd like to do in the talk today is start off by just giving a little bit of background. What is it that actually makes language hard in the first place, and how is it that we've been able to come so far in the last 15 years? How do current systems deal with these difficulties? But then I'd also like to spend a good deal of the talk talking more about my own research. One of the goals of my research is actually to try to address some of the remaining challenges, and the one that I'll focus on today is the challenge of making language technology really inclusive and universal across the world. So let me just start by trying to explain a little bit about what makes language difficult. So let's imagine that we're trying to interpret a sentence like this one. I met the woman in the cafe. Okay. There's a part of the sentence at the end in the cafe, which is I'll refer to as a prepositional phrase because it starts with the preposition in. And if we're trying to understand what the meaning of this sentence is, we need to understand what it is that that phrase actually modifies. And probably the first time you see this sentence, you might assume that what it's modifying is this meeting event, right? That meeting event took place in the cafe. But you might also notice that it's possible to interpret it differently. It could be that the thing that's in the cafe is the woman. So I might be walking down the street, and I see a woman in a cafe, and I turn to my companion and say, I met the woman in the cafe last week in my class. Right? So there's this ambiguity here. And actually, in this sentence, it's a very natural ambiguity. Both of those interpretations are possible. But something that happens a lot with natural language is that actually sentences that have very similar structure to this one, there's really only one sensible interpretation. So I met the woman in the blue coat. Really, it's a bit weird to imagine that that blue coat is where the meeting happened. I met the woman with the blue coat. Again, it's the woman who has the blue coat, but I met the woman with LinkedIn. It's not the woman who has LinkedIn. Well, in a sense she does, but it's the meeting that happened that way. Okay, so this is just one simple example of the kind of ambiguities and resolving those ambiguities that humans are very good at, but it's difficult for computers. And this sort of ambiguity also multiplies exponentially as we get to full sentences, because we not only need to figure out where that particular prepositional phrase is modifying, but all of the connections between all of the words in the sentences. And things get worse because it's not just ambiguity in the sentence structure, but in fact, ambiguity happens at all levels of language. One example, if we're talking about speech recognition, a colleague of mine was talking to a speech recognition system and said, we need more psychopaths on campus. You might wonder why this person said that. In fact, they did not. Right, so here's an ambiguity in the sound of the words that are being said. We can also have ambiguities in the words, the meanings of the words themselves, right? The bank raised interest, depending on how we complete that sentence, could be the bank raised interest rates by 5%, the bank raised interest in its community development program, right? So that word means something different. In fact, there's another word in this sentence that also has two different possible meanings, which you might not have even noticed as a human, because one of them, the financial institution, is so much more obvious, you didn't even recognize the fact that it could also mean a riverbank. Okay, so how do we deal with this? You've probably guessed by that now, given everybody else's talk today, that the way that current systems are dealing with this is basically by using lots and lots of labeled examples. Right? So essentially, if we want a computer system to be able to disambiguate where the right place to attach this prepositional phrase to, we give it lots of examples that have been hand-labeled by humans, saying, in this particular case, it attaches over here, in this case, it attaches here, and so forth. And once we've got all of those labeled examples, we can then train a system by basically extracting features that are relevant that it can hopefully use to then generalize. So the kinds of features that we might get are things like noticing, whether when this word is met, and this word is cafe, does it tend to attach here or here? Whether this word is coat and that word is met, and so forth. And we might also look at, other things like the relationship between the two nouns in the sentence. And in earlier systems, we often built these features in by hand. In more recent neural network systems, these features are often automatically extracted. But the point is that they're kind of doing all of this based on labeled examples. Right? So effectively, what these systems are doing is kind of like this, right? Very schematically, we have a bunch of labeled examples. We feed them into our machine learning algorithm, whatever it is, and we come out with a prediction function. And so over the last 10 to 15 years, what's gotten better about systems is sort of two things. One, we actually, in many cases, have a lot more labeled examples available to us, but in certain circumstances only, and I'll talk about that in just a second. And it's also true that the machine learning algorithms have gotten better. So they're better at extracting relevant information, and in fact, just because computing power has gotten better, we can often use algorithms that we couldn't use before. Okay, so that's sort of where we are today. But I'd like to argue that this does, as I said, leave out certain people from this in terms of universal language technology. So what I've said is that we need to have a lot of labeled data in order to make these systems work. And it turns out that labeling data is very time-consuming and expensive, right? So it's just hard to get that data. Not in all cases, but in many cases, especially for language, right? So if we're trying to develop a speech recognition system, we need to get people to actually transcribe speech into the text. That's roughly 8 to 10 hours of work per hour of speech. And current systems, state-of-the-art systems, often are using hundreds or even thousands of hours of transcribed speech. Okay? Speech is actually not so bad. You can get people to do that. They don't need special training. Things like the kind of syntactic structure that I talked about earlier, you actually need people with special linguistic training to be able to do that. So that's even harder. And what that means is that for lots of languages, these kinds of resources are just not available. So to kind of see how that has an effect, right, we can take a look at current systems. So we can look at something like Google Translate. Google Translate is actually kind of a best case scenario, because in order to train a machine translation system, basically what you need is text in one language translated into another language. And actually, people generate that kind of data all the time for their own purposes, right? The European Parliament, for example, has lots and lots of translations, which they want anyway. And so, in fact, and I should say actually the other big source of this is smaller size, but people translate the Bible all the time. It turns out very popular thing to translate. So we can get these kind of translations. And as a result, Google Translate is available at the moment, well, actually last time I checked, which was about 2 months ago, hopefully this is still true, for about 103 languages. And that seems pretty impressive. I mean, that's a lot better than it was a few years ago. But if we look in a little bit more detail, it's maybe not quite as great as it looks. So about half of the languages, nearly half of those languages are European languages, which clearly doesn't reflect the actual diversity of languages in the world. If we look a little bit more closely in Asia, we see that, for example, there's 22 official languages in India, and only 9 of them are covered by Google Translate. In Africa, there's 5 languages with over 10 million speakers that are not covered by Google Translate. And it's even worse if we look at indigenous languages of like the Americas and the Pacific. So there's 6 million speakers of Quechua, a Native American language. This ranges all the way to many endangered languages spoken in all areas of the Americas. So many of these languages, as I said, are spoken by minority speakers in their area and are often even endangered. It turns out that according to linguistic estimates, there may be roughly 7,000 languages spoken in the world. Right? So 103 is really just a drop in the bucket. And as I said, many of these are spoken by people who are in the minority in terms of their language, also typically in terms of their culture. And so we're basically kind of sending a message that says, you know, your language and your culture is not important for our modern economy. We don't really care if we develop tools for it. And so we're not really encouraging people to keep speaking these languages. And I think that's important not just for sort of cultural reasons, but actually even for scientific reasons. Language preservation and language study is really important for anthropology and for linguistics to try and understand the diversity of languages across the world and what it is that actually causes language to be the way it is. It's kind of a window into our own cognition. Right? So one of my motivations is to try and kind of develop this kind of more universal language technology. And the question is, how can we do that? Right? So ultimately, my inspiration basically comes from the one language learning device that we know of that's actually able to learn all of these languages. Right? And what is that? That's us. So what I do in my research is I think about sort of connections between how we as humans are learning language and what we can build into computer systems. Right? So if we think about human language learning, right, the situation in which humans are learning language is schematically something a bit like this. Right? We get exposed to some speech data in the context of things going on in the world, and we're kind of able to figure out from that what's going on. Right? And that's quite a bit different from the current situation with machine language learning systems, where we kind of tell them, oh yeah, here's the words that are being spoken, here's the relationships between those words, and oh, by the way, this word doggy actually refers to that thing over there. It doesn't refer to the thing in its mouth or part of its tail or whatever, right? So we're giving them a lot more information than infants are using. And so what I'd like to kind of aim for is getting back to trying to figure out, is there a way that we can build computer systems that are learning in a way that's a bit more like humans? Now, you might think that, and actually one point I should make, I'll say as well, is that actually very early on in human language learning, sometimes infants are actually able to learn something about the speech and the perceptual elements of that, even without the surrounding context, although context does become important very early as well. Okay, so you might be thinking, maybe this is all unnecessary, right? There's other cases where we've been able to engineer solutions for problems that are not at all like the natural solution, right? Why do we need to care about what humans are doing with language? Let's just build a language learning device. But I would argue that actually language is different from these other kinds of engineering problems. Right? If we want to solve the problem of flight, what we need to do is we need to understand things like gravity and air resistance and other kinds of physical properties in the world. But I think that's actually pretty different from what's going on with language. Right? Language is not a physical property of the world. It's certainly related to the structure of the world, but it's created by humans for humans. It's a property of our mind. And so I do think that actually if we're going to get to the point of building these kind of computer systems, we really need to think also about human language learning. And so as I said, that kind of leads to this research program that I have of trying to think about machine language learning, build models based on that might potentially give us insights into human language learning, but then simultaneously looking at what we know about humans to potentially build that into better machine learning systems. And what that means also is that much of the work that I do is in a kind of unsupervised or distantly supervised framework, which means that I don't have any particular labels for the task of interest at the time, but I might have some other information available. So if I'm doing, let's say, speech recognition, I'm going to try and not use explicit transcriptions of that speech, But I might use some information like images or information about the context in which that speech occurred, maybe even translations into another language, as I'll talk about right at the end today. And I also want to just emphasize that this research is like definitely more at the kind of fundamental science end of things. We've, I guess, heard talks along this whole continuum today, but I'm not going to sort of get to the end and say, oh, look, here's my application that you can use tomorrow or even in 2 years. I'm definitely thinking much more about the long-term 10 to 20-year timeline. OK, so if we're thinking about things in this way, and we're trying to develop systems that work on kind of unsupervised or distantly supervised ways, one of the things that's really important to that way of thinking is trying to build in good learning biases or inductive biases, right? So people have alluded to this a little bit already today, but I want to just get a little bit more explicit about what that means, right? Because a bias is something that, if you're not familiar with the sort of machine learning way of thinking about this, you think, oh, bias is a bad thing. But actually, bias can be a really good thing, right? If our bias matches the thing that we're trying to learn, it can actually mean that we learn better with less need for observing the data. Right. So just to give a very concrete example of that, let's imagine that I've got a bag of marbles, and there's some red marbles and there's some yellow marbles, and I pull a marble out of this bag, and it's red, and I pull another one out, and that's also red, and then I think, OK, what do I think the probability is that I'm going to pull the next marble out, and it's going to be red also, versus what the probability of it being yellow? It's very hard to make that prediction, right? Because I just don't have that much information. I have no idea how many red marbles and how many yellow marbles are in that bag. If I had pulled out tons and tons, then I could make a good prediction, and I could say, well, it's roughly 50-50, right? But I had to see a lot of data before I could be certain about that, or even close to certain. On the other hand, if I had a bag of marbles and I told you, either all these marbles are red or all of these marbles are yellow, right? That's a really, really strong bias. Now I pull out 2 red marbles, and with very high certainty, I can say the next one is also going to be red because I think basically I have a bag of red marbles. Okay? So the idea here is that the stronger our bias is, right, the less data we need in order to make reasonable conclusions about what's going on. And so ultimately, what I'd like to be able to do is sort of understand more about the biases that human learners have so that we can build those into computer systems so that we don't need to have these gigantic data sets that everybody else has been talking about today. Right? And so to try and illustrate a little bit about how I go about that, I'm going to talk about just one example, initially at least. And this is an example of segmentation. So segmentation is actually something that happens in many different areas of language. So we can segment discourse into topics, or we can segment conversations into speakers, or take a bunch of audio and divide it into speech versus non-speech, and so forth. What I'll focus on right now is the problem of segmenting individual utterances into the words that they contain. Right? And this is a problem that infants actually need to face. It's one of the first problems that they face as language learners. Right? So we've got basically a bunch of audio, a stream that comes in, and we need to figure out where the word boundaries are. Right? Right, so where are the boundaries? And we might want to know that because ultimately, if we're an infant language learner, we need to figure out at some point that those words actually map onto some kind of meaning, and that's useful. Now, you might think that this is kind of a weird thing, like, isn't it really obvious where the word boundaries are? Right? We have this illusion as we're listening to people speaking that there are words there. It turns out, though, that actually there aren't any obvious pauses or anything in between the words. You can tell that because of this example that I showed earlier, right? One way of interpreting that, there was a single word, and the other way, there were actually 2 words, which indicates that there's not an obvious boundary. The way that we're able to interpret that normally is because we know what the words are. But of course, this infant doesn't know what the words are. So there seems to be this kind of chicken and egg problem where to figure out where the boundaries are, we need to know the words, but to figure out the words, we need to know the boundaries. So how do they break into this whole system? So there's a kind of classic experiment now, it's from the mid-90s, that sort of suggested that one of the ways that infants are doing that is using statistical information, which is nice because it means that I can at least fall on the same kind of statistical paradigm that lots of other machine learning is based in, and I know that that's something that humans are probably doing also. So I want to just give you a flavor of how this works. So the way this experiment worked is we had we're working with infants, so we have to make everything very simple, right? So we're going to just take 4 sort of nonsense words to make a little mini vocabulary. And then we can string those words together into kind of like a sentence and remove all the boundaries between the words of that sentence. And then what the researchers did was that they got a computer speech synthesizer to synthesize this speech so that there's no other cues to where the word boundaries are. And they play that to infants for about 4 minutes. And hopefully this will work if I play you an example of what this sounds like. It might be a little bit loud or quiet. Okay, so you can see why we don't do this for more than 4 minutes to the infants. Okay. You can also see that it's not really that obvious where the words are in that thing, right? But it turns out that after listening to that for about 4 minutes, I think it was 4 minutes, I might have that wrong, but it's not very long, you can actually test the infants after that and determine that they actually can figure out what the words are. So the way that you test them is basically you give them little test items in isolation to listen to, and either those test items are words, which are the actual words in the vocabulary, or there are these things called non-words, which actually did occur in this sequence, but really what they are is they're the end of one word followed by the beginning of one of the other words, okay? And it turns out that if you do this, the infants will actually pay attention longer to the words than the non-words. And so by that, you know, because these are pre-verbal infants, you can't just ask them, right? But you know that they actually can tell the difference between those two things, and therefore that they were able to figure out what the words are. And so the researchers proposed that the way that they were doing this was using a certain kind of statistical information, which they referred to as transitional probabilities. And so the idea there is that the syllables here have certain patterns, right? If you hear the syllable to, it's always followed by p because of the structure of the words in the vocabulary. And p is always followed by rho. But when you hear rho, you don't know exactly what's coming next, because it could be any of these 3 syllables that start the next 3 words. So they were hypothesizing that perhaps that was the information that infants were picking up on in order to distinguish between the words and the non-words. And it turns out that that same kind of tendency holds even in real language. So if you look in a large corpus of text, you will find that there is a tendency for there to be a lower transition probability here than inside the word. But it's not nearly as strong as it is in this very simple synthetic example. And it's actually not really quite enough to segment things well overall. And so what we did instead was we actually hypothesized that maybe there's a different kind of process going on here, where instead of focusing on boundaries, maybe what we should be focusing on, and maybe what the infants are focusing on, is the words themselves. So what you'll notice is that if we imagine that our goal is to try and find a vocabulary that explains how this whole thing was generated, we can do that fairly compactly by just proposing the 4 correct words. But if we propose some incorrect words, it actually takes more words in our vocabulary to explain how this whole sequence came about. Okay, so there's this kind of idea that we want to try and come up with a vocabulary that explains everything in a compact fashion. And that's the intuition, but then we needed to actually have a probabilistic model to try and do this. And in addition, we wanted to run this on a more realistic kind of data set than just this toy synthetic data set. So the data set that we used was basically a data set that had been collected of speech that was directed at very young infants. It was actually transcribed phonemically into the sounds, but you probably can't read that, so I've transcribed it here with just standard spelling. And so the idea is that our algorithm gets this kind of thing as input, and then what it's going to try and do is figure out a way to chunk up those utterances into words such that there's a relatively small number of those, and also what it's going to try and do is figure out what the probabilities of each of those are so that it can make good predictions about which word comes next. And actually, this gets back to a similar idea to what I was talking about earlier with the bag of marbles, right? effectively what we're trying to do here is we're saying each of these words is actually like a different color of marble. And what I'm trying to do is pull words out of this bag and make predictions about what color or which word in the vocabulary each of those words is going to be. Right? There's just a lot more different colors of marbles in this scenario. So in this particular case, I've divided things up in a particular way, where there's 25 different marbles, 17 different colors. I didn't actually have enough colors to show them, but each of those black ones is supposed to be a different color. So there's a couple problems, though, that make this harder than the previous marble pulling example. Right? So one, we don't actually know whether the next marble that we're pulling out of the bag is going to be a completely new color, right? A new vocabulary word that we've never seen before. Right? In the previous case, I told you there's just red and yellow, but now we have no idea how many colors there are. And the other problem is that we don't even know how many marbles we saw. So here's where the analogy kind of breaks down a little bit. Right? If I divide up my sequence into different sequence of words, then I suddenly have a different number of marbles and a different set of colors. Right? So the previous example, I had 25 marbles and 17 colors, and now I've got 21 marbles with only 13 colors. So this seems like an incredibly underspecified problem. And that's actually where the idea of having the right bias can really help us. Because if the problem is underspecified, then hopefully if we put in the right kind of bias, it'll sort of guide us towards the right sort of solution. And so the bias that we looked to first was something that's kind of very ubiquitous in language. It's something called Zipf's law. Right? So the idea of Zipf's law, it's actually an empirical law. It's not sort of a theoretical thing. But if we take the words in our language and we just rank them by frequency, right? So the word the is the most frequent word in English, followed by of and to and so forth. And then we write down how frequent each of those words is. It turns out that if we multiply the rank of each word by the frequency of that word, we get something that's roughly a constant. And what that means is that if we actually make a plot of that, we'll see, if this is now on a log-log axis, we'll see sort of roughly a linear correlation here, a linear relationship. And this is something that's not just true of English. It's actually true of all the languages that we've ever looked at. So you can see in lots of different languages this same kind of relationship. So it seems to be something that's pretty universal about language, and so something that's reasonable to try and build into this model. And so that's, in fact, what we did. So we basically used a mathematical model known as the Dirichlet process prior to build in this kind of assumption. And I see that I think I'm going to skip the math here because I would like to get to some other stuff and I don't have a huge amount of time. But basically, this is a way of building in that assumption. And once we do that, we get results that look like this. Right? So it's not perfect. But what you will notice about this is that when the system is proposing boundaries between words, it's pretty accurate about them. On the other hand, it's also missing a lot of the boundaries, right? So these ones in red are things where certainly as adult speakers, we would assume that there should be a boundary there, but it's not finding it. And actually, it's not that surprising if you think about it or if you know much about language, because the reason that this is happening is it turns out, unsurprisingly perhaps, that words are not actually marbles. But specifically what I mean by that is when you pull marbles out of a bag, you're kind of assuming that whatever marble you pulled out last time has no effect on the color of the marble that you pull next. But that's really not true in language, right? So if I pull the word the out of my bag, it's fairly likely that the next word would be something like cat or dog, and much less likely that the next word would be something like eat. Whereas if I pull the word to out of my bag, then actually eat becomes more probable and cat and dog would be less probable. So it turns out that we can actually extend this framework, the mathematical framework, to account for that fact, and we'll get much better results. So our results now look much more like the segmentation that you would expect from this particular text. So that was really nice. And it turned out that developing that mathematical framework was also helpful because we were able to kind of apply it, well, we and also other people were able to apply it to lots of other areas of natural language processing, including things like machine translation and syntactic parsing and various other tasks. And in addition to that, we, in collaboration with some psychology researchers, we showed that this model actually predicts performance on human word segmentation tasks. That is, when we got actual people into a lab, it predicts their performance better than previous proposals. So that seems to suggest that there's something good going on here that actually is modeling what's going on in human segmentation. So that's kind of a extended example of the basic idea of thinking about what are the biases that we can build into these systems. It is, however, fairly old work, so I want to just spend the last little bit of my talk saying a little bit about where I've been going since then. And so one of the things that we've been working on since then is actually trying to think of this idea of segmentation, but at a more kind of closer to the signal, basically. So what I talked about so far, we assume that the input is basically symbols, whether phonemes or characters or whatever. But of course, what infants are actually doing is segmenting real speech. And so some of my PhD students have kind of developed that model a bit further and working from actual acoustic data. And in addition, we're working now on trying to look at methods for what I call perceptual learning, or in the machine learning literature, something called representation learning, which basically means, are there ways that we can kind of process the low-level data in ways that pull out better features at a very low level. And this is also something that is really important for infants very early on. So if you're an English learning infant, for example, you might hear different sounds like L and R, and you need to learn that those sounds actually are distinct in your language, and they can actually represent different sounds that mean different things in different words. So the word lot means something different from the word rot. If you happen to be a Japanese learning infant, you hear those two same sounds, and you actually need to learn that they are not distinct in your language. Right? So this is a kind of perceptual learning problem that happens very early, and we've been thinking a lot about how to kind of model that and potentially use that to develop better speech technology for low-resource languages. And then the last thing that I want to talk about is, of course, the kind of holy grail of language, which is meaning, right? It's kind of pointless to have language technology if we don't deal with meaning at all. So how does meaning fit into all of this? And I think one of the reasons that this is hard to answer is because trying to represent meaning in a way that a computer can deal with it is really not so clear, because we don't really know what meaning is. Even linguists have a hard time on trying to represent the meanings of words and sentences. So what I've been doing recently is actually sort of thinking about kind of a proxy for that. If I can't figure out what the sort of abstract meaning of, let's imagine the kind of Aristotelian meaning of things, maybe what I can do is I can use as a proxy the translation of something into another language, right? So I can kind of represent, if I have some speech in one language, I can represent its meaning in a certain respect by translating it into another language, right? So notice that this is a bit different from a typical speech recognition system, and this is not a transcription of that. It's actually a translation into some other language, right? So I can think of that as the meaning of it, okay? So if I can build a system that can actually learn from this kind of data, then what it's going to be able to do is things like, it might be able to say that, this word here appears somewhere in that speech, and then maybe if I have a large corpus of audio data and I want to find other pieces, other places where that particular word occurs, I can do that because I've been able to map those things, even if I'm not necessarily transcribing them in the typical sense. And it turns out that this kind of data also occurs a lot with endangered languages. So linguists will go out into the field. They maybe, with the help of some bilingual informant, will actually take recordings of people speaking in that language, but rather than transcribing them, they'll actually translate them into a higher resource language like English or Spanish or something like that. Okay, so there actually is data like this. If we were training a sort of typical system to do this kind of task, what we would need to do is actually two steps, right? We would need to first train a speech recognition system using a transcription to go from speech to text in that language. And then we would separately need to train a machine translation system to translate from the text to the other text. So what we're trying to do is basically get rid of that middle step and just directly train a speech system to translate into the other language. And this is kind of work that's ongoing at this point. We have done a bit, and turns out there's another group that's done a bit of work on this as well in a kind of different direction. So roughly speaking, what's happened so far, we started off working at this incredibly low amount of data because we actually were working with a couple of, in fact, endangered languages. So we got this data from a repository of narratives that were told by people in those languages. And we used some fairly heuristic methods, and we did find that we were able to extract a few keywords correctly. So that's certainly promising. At the same time, there was this other group that was working with a much larger amount of data with a not endangered language, so Spanish to English, and a neural network model, and showed that you could get some pretty decent translations from it. So what we're doing at the moment is we're kind of trying to explore this space in between. So we have been sort of re-implementing something a bit like their neural net model and trying to understand like how much data do you really need, what is it good at, what is it not so good at, and try and understand that a little bit better. Yeah, and so that's pretty much what I wanted to say. Essentially that what we're aiming towards is more inclusive language technology, and that requires better learning with less explicitly labeled data. And that to get there, what we need to do is actually consider the only successful language learning device. And so what I do in my own research is trying to build these connections, helping us to design better systems, and also ideally to better understand our own minds. And thanks everyone for listening, and also thank you to my very many collaborators and funding.
That's fabulous. My job as chair has been really easy. They've kept to time brilliantly. So we have time for some questions. And we have microphones. Right, there's one. The member of the Alan Turing Institute there.
Alan Wilson.
Could you say who you are?
It's just switched on, yes. Alan Wilson, Turing Institute. Fascinating talk. Word breaks in human language learning, as I understand it, particular letters might represent the breaks. Question, I've got two questions, and I anticipate the answer to the first question is yes, and the answer to the second question is no. But the questions are these. Could these combinations of words have actually emerged through an evolutionary process in the way language has evolved over time? Mm-hmm. And if the answer is yes to that, and I'm sure that's been explored, could you then use AlphaGo technology to invent sequences of words which might have that property? I'm sorry, those are amateurs' questions.
Right. So I think what you mean is the property that I talked about the particular Zipfian distribution of words. Is that something that has evolved over time? Now, so this is actually an interesting question because there's actually a lot of debate about that. So it turns out that there are some fairly simple mathematical models that have nothing to do with anything interesting that will actually still produce that kind of distribution. And so some people have argued that this process is not at all interesting and really has nothing to do with evolution. It's just sort of a mathematical accident. At the same time, excuse me, there's also arguments to be made about why that might actually be reasonable from an evolutionary perspective. For example, the fact that it's actually not just that there's this distribution on frequencies, but also that the more frequent words tend to be the shorter ones and the less frequent ones tend to be longer. And so there's arguments about communicative efficiency. And there's arguments here about, there's maybe some memory advantage to having this kind of distribution. Or maybe it's even something about the structure of the world itself and what you want to talk about a lot. So yes, it is something that people in the sort of language evolution side think about a lot, and there are simulations that they do. And some of those simulations do actually have a little bit of the character of the ones that Tora was talking about with different agents interacting. I don't know. I think they're probably a little bit less sophisticated in terms of the reinforcement learning part. I have to say I'm not hugely up on the sort of agent-based language evolution side of things, but there definitely are models that people look at in that direction. So yeah, it is something that kind of does relate to this and that people look at.
Two in the front row here.
I'm interested in how you, with this approach, whether it's possible to do sort of noun extraction. One of the classic issues in linguistics is the person pointing from some region. You ask them, "Is that what is that?" And they give you the local word for river, rather than the word for that river. If you're working off sound systems, how are nouns identified and acquired?
So if you're working straight from speech, then you're right. There's nothing there that says this thing is a noun and this thing is a verb. So yeah, so that's something else that I've worked on a lot in my work. I haven't talked about it now, but sort of the question of, if you've got a sequence of words, are there automatic ways that you can figure out which are nouns and which are verbs and what the structure of those things is? I think it's typically assumed that knowledge comes in a little bit later with infants, certainly. Of course, the situation you're talking about is a little bit different because that's more like adult linguists trying to figure things out, or adults. But yes, I mean all of these things are kind of tied in together, and so really part of my research is also thinking about how all of these learning problems kind of mutually inform each other. Because if you know what are the nouns and what are the verbs, that also will help you learn the meaning of a new word in the sentence where you don't know it, but you maybe do know something about some of the other words in the sentence.
Just my information. Are nouns and verbs universal constructs in human language? Are there things we know to go looking for regardless who we're talking to?
Yeah, so I think most linguists would agree that nouns and verbs are fairly universal. Not all the things that we have in English. So prepositions are something that don't occur in all languages. So there are differences there in terms of which parts of speech are universal and which ones aren't. But again, this is actually one of the reasons why language preservation is really important, because actually those kinds of questions are very informative about, if we go and suddenly discover that there's a language that doesn't have nouns, then a whole bunch of theories get blown out of the water. Right, so we do need to kind of understand what the diversity of language is across the world.
Thank you very much.
Okay, one last question down here. Sorry, we need to break for. Oh, well, depends how quick the answer is. We want to break for
This
tea
is
now.
short, I think. So when you back to your marble model and then how you had to improve things,
Yeah.
was that just moving to a bigram model instead of unigram, or?
Yes, it's moving to a bigram model. In the particular formulation of the Dirichlet process, it's something called a hierarchical Dirichlet process, but yes. Yeah.
Okay, that was a quick technical question, so I'll let you finish with the last question then.
Just on the title of the conference, the social good. With this technology, how do we avoid it not being for the social good in the future? For example, language is probably it's been suggested one of the strongest innovations that humans had, and the consequences of that were there was a lot of success for the human race. So it's, in addition, I understand that Noam Chomsky was given a similar project to do in the 1950s, and he expressed some reservations on similar grounds and didn't pursue it as forthrightly as he might have done. Thanks.
Do you get the meaning of the question? Because you've got 30 seconds to answer it. Do you mean how do we train machines to...
Is it so wise to give them all the tools that a human mind has?
Right. Okay, so this is broader than just language, I think. But yeah, I mean, that is certainly a very deep question. And I think that one of the things that we do need to be thinking about was something that I think it was Andrew Blake said in the beginning, which is basically building in ethics by design. And I think that this is not something that many of us have been trained to think about or do in our training over time. And so I do think it's something that's been, many of us are thinking about a lot more than we did even a few years ago. For example, at the the main conference that I go to on natural language processing, there was just the last time there was an ethics in NLP session at that conference, which was overflowing. And that isn't even just about teaching computers to learn language. That was about things like, are we building tools that are accidentally discriminating against people who speak certain dialects because our tools have been trained on the Wall Street Journal, and these people are speaking, not Wall Street Journal, basically. And other there's lots and lots of ethical questions that come up. So I do think that it's definitely much more in the air than it used to be, but probably needs to be even more so, and that as we're training people coming into the field, we really need to be, including that as part of the training.
So that was a very good question to finish with. Thank you very much for raising that point. Thank you, Sharon, for a great talk, and go have some tea.